Thank you, Noelle. I really appreciate this invitation. I'm excited to talk to you all. And I would strongly recommend interruptions and questions. Um, Noelle, is there a time I need to finish by? Um, I know I'm starting late.
Um, if you could, okay. So we were
If I can finish
originally
by
supposed to have
2?
you end at, if you could finish at 2, that would be great. And then we could still have some time for
Okay.
questions. Yeah.
Okay, so I'm going to give a somewhat impromptu and somewhat abbreviated talk. I understand that you have been sent or will soon be sent a few papers that you're going to look at. So, and my role, I think, is to motivate them. There's a story behind this this pathological foliations business that I maybe have a chance to tell a little bit. The papers that I think you've been given or will be given or shown is one is a paper of myself and Michael Schub called Pathological Foliations and Removable Zero Exponents. There's also a paper of me with David Ruel called Absolutely Singular Dynamical Foliations. There's a chapter of a book by Bonatti, Diaz, and Viana. It's a little section where they prove what I'm going to tell you about in a much more concise way than the original proof in the paper with Schub. And there's also a paper that actually came out of, I mean, it's part of this whole story actually, a paper by Jack Milner from the Mathematical Intelligencer called Fubini Foiled. And it gives another example of a pathological foliation of a somewhat different nature than the ones depicted here. So depicted here are foliations of the square. They're actually foliations of the torus, so I could actually identify opposite edges here, and everything would line up continuously nicely. So same here. So what is a foliation? Well, I'm just going to talk today about one-dimensional foliations. There are higher dimensional foliation. A foliation is just a decomposition of your manifold, like the torus here, into lower dimensional manifolds, in this case, curves. And what makes a foliation is that if you look locally at a foliation, it after a homeomorphism, a continuous change of coordinates, the sets in this decomposition just look like line segments, or more generally in higher dimensions, they look like hyperplanes in a cube in Euclidean space, right? And then they can fit together in sort of topologically interesting ways. So here, the sets in the decomposition, which are called leaves, they connect top and bottom to make circles. So this is a foliation of the torus on the left by circles. On the right, these leaves, if you were to follow a leaf around the circle, it actually will wind densely through the torus. So the leaves are lines, and they are densely immersed in the torus. Okay, but they're both foliations, and they're both pathological. And so what does pathological mean? Okay, so I have so F I denote by this foliation. So it's a collection of leaves. I denote a leaf by F of X. That's just an equivalence class containing X. So that's one of these curves. X is in the manifold. Okay, so that's a foliation, like one of these two. And we say it's pathological if there exists a subset, X of M, measurable, such that the Lebesgue measure of the complement of x is 0. But for almost every x in M, or let's say in M with respect to volume, the leafwise measure of x intercept f of x. So if I look at the intersection of x with the leaf through f of x, I'm sorry, the leaf f of x, that's a subset of a one-dimensional manifold, a smooth one-dimensional manifold, and we can talk about the Lebesgue measure of that. And so I'll call that leafwise Lebesgue measure is 0. Okay, so that means, like for example, in the picture of the left, there's a full measure set of the circle, but if I intersect it with almost every leaf, I get something that has measure 0. So that's in contrast to Fubini's theorem. Which says that if you consider, just consider the ordinary foliation of, let's say, of T2, the 2 torus by circles, so in other words, the leaf through a point x comma y in the circle is just x cross S1, or across the vertical circle. Okay, so if you consider that foliation, that's just the ordinary foliation where I draw straight lines instead of these sort of wavy lines. In that case, what Fubini's theorem tells you is that for any set x in T2, if the Lebesgue measure of the complement of x is 0, so if it has full Lebesgue measure, then for almost every xy, the Lebesgue measure of the intersection of x with this leaf f of xy is 1. Because the complement has measure 0, so I guess I should say the complement of, so it has full measure in the leaf f of xy, so the complement f of xy minus x is 0. Okay, so that's Fubini's theorem. That's a consequence of Fubini's theorem. Or more precisely, actually, maybe Cavalieri's principle, which comes from Fubini's theorem. So a pathological foliation is pathological from the point of view of the Lebesgue measure. It has these beautiful, smooth leaves, continuously differentiable leaves, but they fit together in a way that defies the property of Lebesgue, of an ordinary foliation by circles. So that's in contrast to Fubini's. Now, these examples that I'm showing have an even more striking property, which Ruel and I called absolute singularity. I don't know if that term actually caught on. And that's even stronger. It says that there exists a set X of full measure. So the complement has measure 0. And there also exists some integer k greater than or equal to 1, such that for almost every x, y, so I don't know, to distinguish, let's call this F naught, this smooth foliation. okay, because I want to use F to talk about the foliations, these other foliations. If I look at the leaf through XY and I intersect it with this set X, okay, so absolute, I'm sorry, pathological would say that the measure is 0. Um, absolute singularity would say it's K points, it's K, or maybe at most K. In fact, I could, so what that means is that I, for almost every point, if I look at the leaf of the foliation through this point, um, I can select, I don't know, K, maybe 5 points out of the leaf. And if I do this for almost every point, I just do this for the leaf, I actually can build a set of full measure in the square. So it's kind of weird. You think about it, okay? And in fact, you can kind of see, looking at these foliations, where those points would lie. So, one question is like, can you actually see this when you look at, maybe the one on the right is a little bit easier. So you see, I haven't actually drawn all the leaves of the foliation here on the right? So there's these gaps because, I mean, of course, if I drew all of them, it would just be a black square, right? So I just want to give a picture. But what this is giving is actually some sense of what happens if you sort of pick random points and start drawing leaves through those points. And you'll see that there's a whole lot of mass, for example, right here, and very few leaves going through that. So what that means, or what that actually translates into, is that kind of in the center of this opening gap, there's what we call an atom. And that would be a set that's very heavy in the leaf itself, much heavier than kind of it should be, right? And so this kind of opening of gaps like this is kind of a hallmark of these pathological foliations. Okay, so what's the story? I have a half hour. Do I have any questions at this point? You might be like, well, okay, some curious examples. Who cares? Okay, so these curious examples arise from dynamics. They come from dynamics. And this formula here that I've written right here is a way, in my paper with Shub, was a way that we actually proved that these foliations existed. We exhibited an example of a dynamical system that generates a pathological foliation. So maybe not such a, you don't really have to stare much at this formula. I can explain to you where the formula came from. But basically what we started with, if you throw away this term, we start with a map. When B is 0, this goes away. And we start with this map H0, which is just a linear map on the 3-dimensional torus given by the matrix 2, 1, 0, 1, 1, 0, 1, 1, 1. Okay, so this is an example. So this is actually conjugate, linearly conjugate by automorphism of the torus. This is actually conjugate to this map 1, 1, 0, 0, 0, 1. So after a smooth, in fact, a linear change of coordinates, it's actually this map over here. And now, what does this map? So this is on T3. So notice these pictures are on T2. But the example that we demonstrated was on T3. And so what does this look like? Like if I were to draw a picture of the dynamics, Well, let's consider this example here. So 2x plus y, x plus yz. Well, in the first two coordinates, so this is in the xy coordinates, it's this map of the torus given by the cat map matrix 2, 1, 1, 1. So it's a hyperbolic, oopsie, that's a hyperbolic linear automorphism. It's an Anosov automorphism of the torus. But then, of course, there's a z coordinate. And so over every point x, y, we have a circle. I'm drawing a picture of the 3 torus where I'm thinking of it as a circle bundle over the 2 torus. Okay. And this map H naught acts on the whole bundle. And what does it do? So it takes the circle over XY and it maps it to the circle over 2, 1, 1, 1 XY, right? So this is this map, let's call this K. Let's call this map K. So it takes, XYZ, or let's just call this fiber P, goes to the fiber, so P down here goes to the fiber over K of P. Okay, so it shuffles the fibers around in a chaotic fashion given by this matrix, but then it's just trivial on the fibers, just the identity on the 3rd coordinate. Okay. So this is a really nice example of what we would call a toy model in dynamics. It's a dynamical system that has kind of 2, in this picture at least, kind of independent things going on. There's hyperbolic dynamics in the horizontal direction, which is chaotic, and there's trivial dynamics going on in the second direction, which is very far from chaotic. It's trivial. It's the identity map. And we've just thrown them together into a single map. And you might ask, kind of in the dynamics of this example, what wins, the chaotic features or the trivial features? What do I mean by what wins? Well, is this map chaotic or trivial or some mixture of the two? I would argue it's a mixture of the two. Like, it's not ergodic because, or transitive. I'm using terms which I'm hoping if you'll stop me if they're unfamiliar. But if I take like a slice of this 3 torus bounded by 2 horizontal tori, that's an invariant set. Okay, it doesn't mix up. Okay, so it's in some sense not very chaotic from that point of view, but there is this chaotic sort of base action going on. Okay. Question. I don't know the definition of ergodic. Okay, guess what? You don't need to know. How about transitive? Do you know transitive? That's good. Okay. So we're going to stick with transitive. Ergodic is just a measure theory version of transitive. So this paper does, because it's about measure, it's involving measure theory. Okay. So I'm going to try I'm going to try to stay pretty loose because now I have 23 minutes left. Okay. So I'm going to try to stay pretty loose with this. Okay. So the question is, with this toy model, what happens when you perturb this? Okay. Well, there's the first thing I can do, which is I can set B not equal to 0. And then I have this map HB. Okay, so it looks identical. If I go up here, it looks identical to H0, except there's some twisting that's going on in the 3rd factor, right? So this is basically H0, and then plus I do, so H0 of XYZ, plus B times some function of, did I make it a function of X and Y? Okay, so this is what we might call a skew product. And what does it do? it takes this, it does the same thing. It doesn't change the action in the base. So in other words, if I take a point P down here and I go over to K of P, the circle over P in the torus, in the 3 torus, will go to the circle over KP. But now there's going to be a little twist added. So like if this is a point Z, Z is my third coordinate, and now it gets shifted by a function of the first 2. So this is called skew product. And this is an interesting thing. It still has these circles that are invariant, but now the dynamics, I've just sort of, what I've done effectively is I've mixed the dynamics of the base and the fiber. That's a way of saying it. I've kind of pushed some of the base into the fiber. So it affects the fiber. The base is chaotic, the fiber is not, but now H0, the first matrix, or the block is H0 the first matrix or the block diagonal? No, it's the first matrix, but the first matrix actually also preserves the circles. It isn't the identity, but it twists, but in a way that doesn't really affect the dynamics in the fiber. So yes, H0 is actually yes, H0 is not this over here. I'm sorry. So this, I'm going to call this H0, and this is conjugate to H0. Okay. But anyway, so now this twists, and now for basically a typical phi, so for basically almost any phi, in a way that I won't, like if you pick phi at random, generically, this map H sub B is now transitive. It has a dense orbit. It's also ergodic. Almost every orbit is dense. Okay, so by just a weird little mix, I've suddenly created, I've pushed some of the chaotic behavior now into the fiber, and now I have dense orbits where I didn't have dense orbits before. Okay, and then there's a second perturbation, and the second perturbation, let me just describe in words what it does. Okay, this is, I'm going to, so I take HB and then I compose it by GA. What does GA do? In pictures. So GA, so down here we have a pair of foliations, stable and unstable foliations, or they're lines. For the initial map K. And up here we have, so let's call this the unstable direction. And then the other one is stable. And what we do, what this map GA does, and it turns out the specific form of GA turns out really not to be important. But let me just draw, this is kind of a slice of the torus over a piece of this unstable line. This unstable line winds densely. But I'm going to just draw, like, this is a little cylinder, right? These are all circles. Okay, the dynamics of H, well, it does something like this. Now I'm going to lie about H0, and I'm going to say H0 is just the one that's like acts trivially on the third direction. What does GA do? It mixes. It mixes in some way that can extend globally, GA mixes, i.e. rotates, or it acts as a rotation, or a kind of it's a rotation in some coordinates, sometimes in some directions, in some places in other directions, but it mixes the vertical, which I call center direction, with the unstable direction, which is horizontal. And so what I do is I take my map, my initial map, which is just apply A and do a little bit of a rotation, and then I compose with this G, and what this G does is it preserves this, so it preserves these, what I call center unstable slices. And actually, let me show you a picture, because the actual form of the map is not really important. Let me show you a picture from a paper. This is from a paper I wrote with Artur Avila and Sylvain Crovizier on what seems to be a completely different subject, but we use the same type of perturbation. And so you can think of this direction here as this, what I'm doing in yellow, as being this unstable direction. Maybe yellow is not the best. This is an unstable direction. And this vertical here is what I call center, which means it's not expanded or contracted in this case. And you imagine, and this is the other direction, which is stable, right? And I could actually do the perturbation that I just described locally. You don't actually have to do globally, like in the formula I wrote. And locally, what this perturbation does is it's supported in some kind of ball, and you slice this ball along the center unstable directions. And inside of these directions, you see what I'm doing here. This is a picture of what the map does. It twists sort of close to the origin, it twists linearly. And as you move out, then the twist goes to zero. I mean, it twists less and less. But basically, it's just a rotation. It's just twisting one direction into the other. Okay. So, and then it doesn't do anything. It's the identity. It's completely trivial in this direction. Okay. All right. Well, what does that do? Well, think for a minute just from linear algebra. From linear algebra, what you're essentially doing is you're taking a map that maybe looks like lambda 0, 0, 1. Okay, this is just in the center unstable direction. And I'm composing it with some kind of rotation, like cosine theta, sine theta minus sine theta, cosine theta, something like this. What does this rotation do to the eigenvalues of this matrix? So I start out with eigenvalues 0 and 1, and now I'm going to do an impromptu calculation, which could like get me in trouble. So so I have lambda cosine theta here. I have sine theta here. I have minus lambda sine theta here, and I have cosine theta here, right? So if I do a perturbation like that, we're talking about linear algebra, just on the level of a derivative, basically. And now the characteristic polynomial is x squared minus lambda plus 1 cosine times x plus, and now the derivative remains lambda, right? Because the derivative of this on the thing on the left is 1. The derivative is lambda equals 0. Okay, and so the eigenvalues are lambda plus 1 cosine plus or minus the square root of lambda plus 1 squared cosine squared minus 4 lambda squared all over 2. Okay, so when the cosine term is 1, so when C equals 1, so is anyone going to stop me and tell me I've done anything wrong? I haven't, right? Cosine, good. So when C equals 1, you're going to get the eigenvalues 1 and lambda. But when C is a little bit less than 1, what happens to this eigenvalue and this eigenvalue? Well, when C is 1, someone can plug this into a linear algebra program. Well, let's see, what happens when C goes to 0? When C is actually 0, then the eigenvalues actually become imaginary, right? But when C is just close to 1, I believe that this one goes up a little. I think there's a picture one can draw here. And it's basically this one. We have an eigenvalue lambda, we have an eigenvalue 1, and as C varies, what happens is these two come closer together. At some point, they collide, and then they head off into the complex plane. Okay? So when C is 0, they're actually, plus or minus 2 lambda I, or plus or minus lambda I. Okay. And so in effect,
Could I ask a question on your last slide?
yeah.
I'm just wondering, in your quadratic formula, is it for lambda or for lambda squared? I just wasn't sure because
it's for lambda.
Okay, cool. Sorry. Thanks.
Right. Yep, you're totally right. Yep. Okay. So anyway, this is going to get a little bit bigger, and this one's going to get a little bit smaller. So this becomes less than 1, and this becomes greater than 1. Okay. Or this becomes greater than 1. Slow myself down. And this becomes less than lambda. Okay. So a little perturbation changes them. So what happens when I do this globally? What happens when I do this in this global perturbation? So that was just a linear algebra. What happens is, so the effect now of composition with this G alpha, or G beta, GA. So what is the effect? Okay. Well, basically, I'm going to replace eigenvalues by something called Lyapunov exponents. Okay, because that's a global thing that you can measure when you're looking at what's called a volume preserving dynamical system. Okay, and what are these Lyapunov exponents? Well, there's a theorem of Osladet's that applies to these examples. And it says the following: there exists a splitting of the 3-dimensional tangent bundle into 3 subbundles. This is, so let's consider FAB, okay, where A and B might be 0 or non-zero, and this is this composition of GA with FB. And A and B are small. Let's say positive, but they don't have to be positive, but they're small. So I get a splitting into 3 bundles. And if I take a vector and there exists 3 numbers, they're real numbers, lambda U, lambda C, and lambda S. Lambda U is bigger than 0, lambda S is less than 0. And with the property that if I take V in one of these E's, like EU or EC or S, of norm 1, then the limit as n goes to infinity of the 1 over n times the log of the norm of the derivative of FAB to the n applied to V. So that's the growth rate, asymptotic growth rate. This exists and equals lambda u. Okay, so I have to qualify what I just said. So I take V and E star. Well, let me move this out of the way a little bit. Okay. In fact, what I want to do is take for almost every x in T3 with respect to Lebesgue. If I take that bundle, and I take a vector in that bundle of length 1, then this is the growth of the vector under that iteration. And this is called a Lyapunov exponent. So it's sort of like the logarithm of an eigenvalue. I probably shouldn't have used lambda since I used lambda here for an eigenvalue, and here it's more like log of lambda. Okay, so what is going on here is the following. So let's look at values of A. So let's look at FAB, and let's look at the Lyapunov exponents. So there are lambda UAB, lambda CAB, and lambda SAB. So these are expansion contraction rates. So when A and B are 0, then these 3 are constants. This is the log of some constant I'll call mu, which is like 3 plus root 5 over 2 or something. This is 0 because if I take a vector in the vertical direction, it doesn't expand or contract at all. And this one is minus the log of, because it's contracting, log of the contracting eigenvalue. Now, if I let B, I keep A equal to 0, but I take B not equal to 0, then believe it or not, these things don't change at all. Okay. Recall what happens here dynamically is I move these circles around according to the dynamics of the base, and I put a little rotation, and it varies from point to point, how much I rotate. And so there's no expansion in this direction, right? So log of 1 is 0. But what we prove is that if I take B not equal to 0, and that actually is not the important thing. The important thing is if A is not equal to 0, so lambda S, which remember that's this direction, which doesn't get changed at all by the perturbation, it stays the same. So this is still minus log mu. But then the effect on the exponents is very similar to the effect of the eigenvalues in my little linear algebra problem. And so what happens is this becomes a little smaller than log mu, and this becomes greater than 0. So let me summarize. And so this is what we proved. Shub and I proved this. And there's a whole story that I'm not going to have time because I have 3 minutes. So, but we proved this. But what's the consequence of this? So the consequence is that after perturbation, so there's something closely related to, there's a kind of structural stability. Now, we didn't prove this. This is, it's a sort of a partial structural stability. So this was proved by Hirsch, Pugh, and Shub back in the 70s. But after perturbation, what happens is I have a new foliation, no longer by these straight circles, okay? But I still have a new foliation that's invariant. Invariant by FAB. So just like in the old case, and you can project them down to an ordinary torus in a continuous way, so that on the base, FAB continues to look like K, but now these circles are permuted in a way that's diffeomorphic it's a diffeomorphism on fibers. It's no longer a rotation. And I continue to have EC, but EC is now actually tangent to these fibers. And I have an EU and an ES, just like I did before. So this is a partially hyperbolic system. And now for V inside of EC, I get that the limit as n goes to infinity of 1 over n times the log of the norm of dFAB to the n applied to V, the nth derivative, now that's positive. Before that was 0. So the center, these circles, have, by this silly perturbation, they have borrowed hyperbolicity from EU. Just because I rotated, I put a little rotation in there. And now this is what causes pathology. So it is 2 o'clock. And I've told you a lot. I was supposed to motivate this, but instead I explained it, which that's fine, I guess. But this is what causes pathology. It's the production of positive exponents. And the reason is, let me just say in words. Everyone can see me gesturing here. Am I big enough? Maybe I should, well, okay. The reason is, take almost any point. Okay, I can say it in words. So I take almost every point, P in T3, and I consider this circle, let's call it FC of X, of P, sorry, through P. Okay. Then so take such a thing. Now suppose, and I want my X, sorry, I have to define my set X. I let X be the set of all P such that, star holds. So again, I should have said this is for almost every P, very important. This is the oscilladets. So if I let X be the set of P such that this holds, and now I look at X intersect FC of P, I want to claim that has measure 0. But what if it had positive measure? Well, if the Lebesgue measure, 1D Lebesgue measure of this were positive, I'm getting one person nodding, I like that. So if it were positive, then if I were to apply FAB to that circle, I go to another circle. But at all these points where this limit exists and is positive, the limit is always non-negative, okay? But at the points, well, that's not true. But if I look at the points where it's positive, I don't care if there are points where it's negative, that set gets bigger, right? By the change of variables formula, it's controlled. What happens to it under n iterates, the measure of it is actually controlled by this norm of the derivative. And so as I go, this is growing exponentially. And so eventually the measure of that set inside of the circle gets larger than the measure of the circle, the length of the circles inside the foliation. Contradiction. Okay, so the set of points, almost every point has this expansion property, but it can't meet a circle in a set of positive measure because that will blow up the circle under iteration. And that's a contradiction. So that the big circle, too big circle, and that's a contradiction. And what you can show is even something stronger, which is this set X is going to meet each circle, almost every circle, in finitely many points. And that uses something called Pessin theory. Okay, I know it's 4 minutes after, but what I wanted to say is the whole pathology thing is kind of curious and weird, right? But in some sense, what's more interesting, at least from my perspective, was the ability to change exponents like this under a perturbation by rotating this unstable into the center, for the center to steal hyperbolicity. And this is a technique that Avila and Corbusier and I used to prove that the C1 generic volume preserving diffeomorphism with positive entropy is ergodic. So we were able to start with a diffeomorphism that has positive entropy, which is the same as saying you have positively Lyapunov exponent somewhere. That's all it means. So same kind of thing. You have a vector somewhere, some positive measure set of vectors where you see expansion. And we're able to take that and sort of spread it under like a robust or strong kind of perturbation, spread that expansion all over the manifold, and then make that expansion in all, or contraction, because there could be, but make there be expansion or contraction in all directions. And that's a very strong kind of hyperbolicity that we found was generic, just starting with a positive exponent, positive entropy. And it uses, as I said, this picture is exactly the same type of perturbation, but now we used it in this kind of context. Okay, I'm done. Thank you. Sorry for going over.
Okay, thank you so much, Amie. I think we have time for a question if someone would like to ask one.
Can I ask a question then?
Yes.
So apparently the thing that allows this for pathological foliation in this case is we basically got a hyperbolic system, like an unstable direction, such that the unstable foliation is not an immersed disk, it's actually a compact manifold. So
Right, except, yeah, right. Is that bizarre? I know that's not your question. We would call this a center foliation, but it's,
yeah.
as you said, it's sort of behaving like an unstable foliation, and right, in that sense. It's tangent to a direction that is non-uniformly expanded.
Okay, cool.
So is that your question?
Yeah, I just wanted it to clarify that, yeah.
Yeah, and in fact, this picture, you can also see this phenomenon in certain foliations where the leaves are not compact. So this phenomenon does also occur even when you don't have the compactity, but there's a certain compactness behind the phenomenon in at least some of these examples. But yeah, that's, you exactly put it on the nose. So the original name of our paper was a stably Bernoulli diffeomorphism that's not a Nossoff. Because what this gives you, this FAB gives you non-zero Lyapunov exponents. None of them are zero. And this implies a property combined with ergodicity, which you have. This gives a property called Bernoulli. And the fact that this center exponent is non-zero is actually stable if you perturb further. You can show that it's because it's an integral of a continuous quantity over a foliation that varies continuously. And so you get a diffeomorphism that has this Bernoulli property, this ergodic theory property, and it remains that way under perturbations. But it's not an Anosov diffeomorphism. Like this one direction is has compact leaves. It's not. So, but then the referee thought we should play up the pathological angle.
Thank you.
All right, I think with that question, we are going to stop things here so Bryna can get set up. Thank you again so much, Amie, for coming in this morning.
Thank you, Noelle.
Right.
Okay, I will stop sharing. There we go.